Any questions about what we've been doing so far? So just a brief recap. The structure of a discrete event model, which is one thing, which is that the main item of interest is the event. And what the event does is the event performs a state transition, which is instantaneous in terms of simulated time, and it schedules other events, or it may schedule other events. It may schedule them unconditionally, or it may schedule them only if the simulation is in a particular state. So that's the structure of discrete event. And there are, just an FYI, there are a number of different so-called world views, ways of looking, ways of kind of creating these models. And the one that we're presenting here is based on something called event graphs, in which the event, the state transition, is represented as a node in the graph, and the scheduling relationship that is represented as an arc or an edge. In graph theory, evidently, there are these kind of dueling terminologies. So there's nodes and arcs, and there's vertices and edges, and I always get them confused. So, so node and vertex are synonymous. Arc and edge are also synonymous. And also in graph theory, you can have either undirected or directed edges. And in event graphs, they're always directed. They're directed because the relationship between one event that schedules another is a directional one. It's not, if you have an event that gets scheduled by another event, that event just in that relationship doesn't schedule the previous one. Now it could, there's nothing to prevent it going both ways. If that's the case, there would be two arcs, one from the first to the second and another from the second back to the first. And sometimes that comes up. The other thing to remember about these scheduling edges is that they have some attributes on them. One attribute, the most important one, is the time delay. That is the time between when an event occurs and the time that the event it's scheduling is going to be put forth. And that's always the current simulated time plus that amount of time. The default is 0. So if there's no time listed on an event, then it's assumed to be 0. The second attribute that we've seen is a Boolean condition. And what that means is that if when that event occurs, that Boolean condition is true, then the event at the other end of that scheduling edge does get scheduled with the appropriate time delay. And if the Boolean condition is false, then it doesn't. And the important thing to remember about that is that you get one shot. That is, now, given, as you've seen, an event can occur multiple times, but for one occurrence of the event, either that Boolean is true or it's not true. If it's false, then the other event doesn't get scheduled, and the event, that's it. It doesn't sit around waiting for that to be true. Okay, and I say that because that's, in the past, sometimes that's a misleading idea that sometimes shows up. And now, as we go along, we're going to be adding a little bit more to that methodology. Not today, but going forward. Actually, I mean, it turns out that just using what we've had so far, you can literally create anything that is creatable. The problem comes is that sometimes, even though you can do it in a certain way, it's not very conducive to understanding what's going on. In other words, it's like you can write every computer program without using arrays, the concept of an array. Don't need it. Well, instead of an array, you can have, variable, x1, x2, x3, x4, just as different scalar arrays. You don't need it. Okay, but why have an array? Well, because you can write much more, much cleaner, more understandable programs using that. And the same is true of some of these things that we're going to be adding in to our scheduling edges. And then there's one more type of edge that we're going to add a little bit later, which is called a canceling edge. And and again, it isn't strictly speaking necessary, but it helps create models that kind of look cleaner. And you say, well, what is so important about having a clean looking model? Well, it's like, well, again, getting back to the arrays, one of the benefits of an array is when you look at what the logic is, you can figure out what it's doing. If every index had a different one, you would have these long if statements and all kinds of clutter that gets in the way of understanding what the thing is doing. The power of these event graphs is you can look at the event graph and understand, once you understand what's going on with these, you can understand to a certain extent what that piece of it is doing. So now to that end, there is, let's see, where was it? Okay, last time, okay, can everybody see this? Last time we wound up with the a model in which we recognized that our multiple server queue model, just in its plain vanilla form, didn't capture an important characteristic of the system we're modeling. In this particular case, the system we wanted to model had a finite capacity of waiting. And the way that the behavior of our so-called customers is if they came and there was no room at the inn, if the capacity of the queue was full, then they left. And that's also an assumption, which isn't necessarily true for a particular system. In other words, if you're in kind of a monopolistic situation, maybe if you're the only game in town and the customer can't come this time, maybe they'll go away for a while and then come back. Okay, this model doesn't do that. This model assumes that we lose them. Okay, which one is correct? Exactly. Neither one's correct. It depends on the situation. So, and the other thing to understand is that none of what is here is a law of nature. The only thing that comes close to a law of nature is this run event. And that run event is just a convention, just like the main method in a Java program, or which borrowed it from C, and even in Python there's an underscore main underscore that you can use. So okay, so this is where we wound up with this model. In other words, we had to split apart the arrivals and joining the queues because that was a little bit different. And then we had to add in a state variable about counting the number of times that we lost a customer. And the thing about that was the measure we were interested in was what percentage of our potential customers are we losing because of this? And that would allow us to ask of this model, well, how would that percentage change if we were to say add one more customer worth of capacity? And then we could make that trade-off. In other words, we could use this model to address that question. Now, one thing that, models are stupid things. They're just as stupid as computer programs. And you may have heard me say last quarter that computer programs are so stupid that they do exactly what you tell them to and not what you want them to. Simulation models are the same thing. They do exactly what you've told them to and not what you want them to. So there's a boundary condition here that I didn't have a chance to get to last time. And what is that boundary condition? Well, that boundary condition has to do with the capacity. So we said, well, what if there's a finite capacity? Well, what if there's no capacity at all? What if there's no queue whatsoever? Now, you might have to ask your grandparents about this, but there used to be a thing called landlines. That's when your phone was literally, it was like, it would be like on a wall. So it's like, I mean, back in the day, you never heard the sentence, "I lost my phone," because it was attached to the wall. Now, in those days, if you made a phone call and at the other end, they were on their phone, you got a busy signal. That was it. And it used to be when you called customer service and they were on the line, you got a busy signal, and you could wait on that busy signal forever, because even if they hung up, it just wouldn't happen. The voicemail kind of came a little bit later, even before cell phones. But it's like back in the day, they didn't have that. So there are situations that you could, if we were back in that day modeling that particular system, say, well, what if there was zero capacity for queue? So, well, we have a model that does finite capacity, but what would this do? So we because we can kind of be the event, you've already been the event list. So let's look at what would happen if we tried to run this model where C, the capacity is zero. So we'd schedule the first arrival. Okay, now at some time later, that first arrival would happen. It would schedule the next arrival, and it would check this Boolean condition. What's the condition? Q is less than C. So what is for that first guy, how many are in the queue at that point? What is the value of Q? 0. Why? Because it was set at the run and nothing else has changed. What's the value of C? The capacity is 0. So what is the value of the expression Q less than C when Q is 0 and C is 0? False. It's always false. So in other words, if we were to run this model with no capacity, we would get a bunch of arrivals, but basically everybody would balk. Nobody would come into the system. Okay, so in other words, this model doesn't work for those values of those particular parameters. And that sometimes happens where you have a model that works for certain admissible parameters and other parameters are not. So in this particular case, we need a slightly different model. Well, we could actually kind of tweak this a little bit, but what's even simpler is, well, first of all, if there's no room for a queue, we had a variable Q that was the number in the queue, but if there's no queue, why even have that variable in the first place? So if we have our state variables, the number of available servers, the number of bulks, and the number of potential customers, as before, then if we look at so here we have our arrivals kind of churning. But now look at, we don't have a queue. So here, for this model, the criterion was based on Q, but we don't have Q anymore. So what is the criterion? Well, if we arrive, under what condition can we actually start service right away? And that's if there's an available server. So we show up, if there's an available server, we can start service right away. And if not, then too bad. And so if there's an available server, we can schedule service, start service right away. If there isn't, then we balk. And now here's the other thing. They notice that in this one, there was an edge from end service back to start service. But here, because there's no queue, how can end service schedule anything when there's not going to be anybody there? So, and this was a non-trivial thing back in the day. It's like, so if back in the day there was like one telephone company, it was monopoly and all that. So if you're the telephone company and you're sort of setting the capacity for the number of of connections that you can have. There's only a finite, and it used to be. So they tried to set it so that most of the time when you call up, you would actually get somebody there because the connection could physically be made. You go back even further. Remember, you had the operators with those little wire things they stuck in the wall. So there's a finite amount of those. If they're all plugged in and you want to make another connection, there are no wires. So, but back in the day, on Mother's Day, which was the peak day of the whole year, you couldn't necessarily get through to your mom. Why? Because all of the circuits were busy and you couldn't get one. Okay, so that's all right. Now we're ready to start today. Yes, question. Was that there? Oh, no, you're absolutely right. Let me, that's a little overzealous copying and pasting. So yeah, that is nonsensical. I will correct that and upload a better one. Thank you. Yeah, this should have been S equal K. That's what this should have been. Thank you. Okay. Better keep those. All right, so now going to move on to just a few more. Okay, so today's models are, we're going to look at a slightly different assumption. So let's see. So can this be seen by the folks online?
Yes.
Okay, thank you. Because when I went to share it, it offered me 2 desktops. So I flipped a coin and picked one. So glad I picked the right one. All right. So today we're going to look at tandem queues. So in our basic model, what happened when a customer left the service, they went away and we were kind of done with them. But what if we're in a situation where instead of leaving altogether, they actually join another queue? If you've ever checked in anywhere, that's probably, or gone to, say, DMV, I mean, you have actually a whole sequence of these. So we'll start with 2 and look at 3 variations of this. So this is, I think, the meta message I want you to get is that none of these models are sort of necessarily the finished product. That is, you always want to be looking at the assumptions and say, well, is this really matching the way our system works? And if it doesn't, then you tweak it. So we'll, okay, so a tandem queue, you know what a tandem bicycle is. So tandem is like 2. So the idea is that you have one set of servers that has a queue in front of it. The customers, they get service from the first guy. And then when they finish, they then go to a second bank of servers that also has a queue. And we're assuming that both of these are, sort of visually, it might look something like this. So in other words, like in this particular case, there are 5 servers in the first bank and only 3 in the second. So the number of servers in each of the different queues is going to be potentially different. So we want to capture that. We have 2 different queues here now. So the state of our system or the state of the simulation, when we look at it, we can't, or one number is not going to be sufficient to describe what's happening for the customers who are waiting. Because in this case, there are 3 customers waiting in the first queue and 2 customers waiting in the second queue. And so one number is not going to cut it for that. We need at least 2 numbers. And furthermore, I mean, in this case, given that there's a queue, that means that all servers are busy, period. But let's say if there wasn't anybody waiting here, let's say that there were maybe only 2 waiting here. So at the second station, there was the value of, there would be 1 available server here and none at the first. Okay, so this is, so the idea, and in my experience, the power of incremental modeling is that you can be informed by the previous model, but you don't want to be handcuffed to it. So informed by the previous model. So yeah, well, and then here's the important difference between the way that customers arrive. So customers to the first station, they're arriving from the outside. So they have this sort of arrival process or Poisson process, if you like to think of that as coming in there. But at the second station, it's not a Poisson process. It's a process which depends on how customers are exiting that first system. And that's much more complex than a simple arrival process. In fact, for the general arrival process, there isn't a nice formula that you can use to describe this. Even when we're simulating for our arrival process, we have a nice, if you will, formula. The formula being the random variable that are the inter-arrival times. So we can kind of pre-specify that. But the nature of the arrivals to the second one depend on how customers are arriving here, how the service time is, how many, all the characteristics of that first station go into how customers arrive to the second station. And there's no simple way to describe that. So that's an important difference. So having said that, now we have enough information though to describe our parameters. And that's where, again, when I make you do it, which will be very, very soon, this is the way I strongly encourage you to go through this, just based upon, because whenever, well, let me put it this way, whenever I do something else, I always get wrapped around the axle. And now you may be more adept at this than I am, but caveat emptor. Okay, so the inter-arrival times, see, we have the customer still coming in from the outside. And again, that's an assumption that we're at one point we're going to really take a look at. So because we have 2 stations, we're going to have, as you saw in this example here, we need 2 different parameters, one for how many of the first station, how many in the second station. And how do we index them? Do we index them the logical way, like 1, 2, 3, or we index them the stupid programming way, which is 0, 1, 2. So pick your poison. The advantage of using the silly 0-based indexing is that it's going to be easier to turn this into a working model. Because as you might guess, kind of looking down the road a little bit, the thing that should maybe occur to you is like, well, wait a minute. This is kind of like that scalar thing where we're giving a 0 and a 1 and a 2. So we can maybe turn that into an array. And if that's how you're thinking, that's good thinking. But for now, we're just going to stick with scalars. The other thing is that the service times are going to be different typically, because they're typically 2 different tasks. Another use case for this kind of thing would be like a fabrication shop where you first have to do one task on one kind of machine and then have to do a similar, another task on another kind of machine. So it might be welding and grinding, or it might be drilling and then cleaning, just with the two. So those are the two parameters. I'm sorry, the 2, 4, 5 parameters. And then in terms of states, as we need different states for the number in the queue at the first station versus the second station. And furthermore, we need a different set of states. And I noticed that I have incompletely defined my states here. So the number in the queue at the first station, number queue at the second station. Those are going to be two different quantities typically. And furthermore, the number of available servers at the first station, initially that first K0, or the number of available servers at the second station. Okay, so this is and for this model, that's so far, that's all we can sort of think of. We could maybe add, you could add in a few other ones that you can think of, like the number in the system at the first station. We could call that L0, and the number in the system at the second station, the Q plus in service. But as we've seen before, that's a so our L0 would be the number in the queue at 0 plus K0 minus S0. And similarly, at the second station, we would have exactly the same thing. Oops, that is a 0. So we don't need them. We could put them in if we wanted, but I'm not. Why? Because I'm lazy. Correct. Or if I didn't have L0 and L1, it would be the sum of those things. Yeah, exactly. Yeah, in other words, there are kind of, for a particular way of modeling the states, there's sort of essential states and derived states. So in these, the Q's and the S's are essential in this way of doing things. But the L's, the total numbers, are derived, and so they're redundant. For small models like this, it's not the worst thing in the world to add them in. But in general, particularly when you get to larger models, whenever you have redundant or when you're explicitly putting redundant states in, it usually messes things up. That's not why? Because when you're developing a model, there are a lot of changes that go on, especially with a larger model. And then if I have derived state that's being explicit, then if I change one, then I have to change the other everywhere. And that's so. I mean, in a way, it's we didn't really get into this, but if you've ever dealt with databases, if you remember, there's something called normalized databases, which is where every piece of data is represented exactly once in the database. And it takes quite a bit of doing to make sure you do that. And there's something kind of similar here. In other words, a normalized event graph model would not have any redundant states, that is, states that are dependent on the other. Now, was that always such a good thing? You can think of circumstances where it actually helps to have these other states. But okay, so now if you remember last time, I kind of went through and did everything by hand. Here, I'm gonna cheat a little bit today with this because it's fairly straight. It should be fairly straightforward, but I go through the same process, and I encourage you to do the same thing. In other words, we start with the run event, and the run event is going to begin always by initializing our state variables. So if we have defined them correctly, which means that we include the initial conditions, then we can always write this run event. And if we can't, then that means that we haven't sufficiently defined our state variables. So that's reason number 52, why parameters and state variables should always be defined before you even start drawing the events. And the thing is that this is the advantage of this is that once we do this, then the page isn't blank anymore. And so we can at least get over that first speed hump of putting stuff in. Now, informed by if we're informed by our previous multiple server queue model, we see that here we have we just have arrival 0, start service 0, end service 0, meaning that these are changing the states at the first station. And at the second station, we're basically doing the same thing, except for the state variables associated with the second station. Now, in general, though, I mean, just in general, that's how this model works. For other models, it may be the case that you have events that actually have state transitions for both, in both ones. That is, there's no law that says that these have, if I call something arrival 1, that it has to be only this one. The other thing to understand is that the numbers, the 0 and the 1, those are actually part of the name. They're not like parameters. A little later, I'm not sure how much later, at some point we're going to talk about adding parameters, which are going to be like arguments in methods, but that's not what's going on here. The name of this event is arrival 0. That's the name. The 0 is not an argument or anything. And in fact, logically, it can't be an argument. Arguments are never a number. Arguments are always a variable. Okay, so this should look somewhat familiar, but then here's the thing. Here's how we work with it. Well, you pick an event, and I'm gonna do this. Just how should I say? It's like I'm going to kind of walk through the whole thing. So run is going to schedule an arrival with an inter-arrival time of our inter-arrival times. And what does arrival here do? It schedules another one, first of all. And it may schedule a start service. And hopefully this is not too quick, but we've kind of done this for the multiple server queue already, right? So, and now my start service will schedule an end service with a delay. Now my delay has to be S0, that is the service time at the first station. And an end service may schedule another initiation of service, but only if there's some in that first queue. There could be some in the second queue, but that isn't going to count. And then just as, see, in a way, just as when you're taking a test, you should always do the easiest ones first and then the harder ones, because that'll maximize your score for a given level of studying. Same thing here. In other words, pick off the easy stuff first, because then it'll be down. What's the easy stuff here? Well, the easy stuff is that this second thing, once I have an arrival, then I can do exactly the same. Oops, bigger than 0. The same logic here. And now the delay is simply the second service time. And then if there's somebody in that second queue, and it's important to take this sort of slowly and maybe sort of talk yourself through it, at least in the beginning, because and the reason I say that is because there's kind of a tendency to just kind of say, okay, well, the other model was like this, and so we're going to just kind of do it the same way. But it should always be, is this what's happening for this particular model? Now, some reason I can't change. All right, so now, and then let's look at this and see how is this model going to behave? Well, we have our run event. It's going to schedule arrival. It's going to schedule another arrival. Assuming that we have our Ks in place, it'll schedule a start service. That'll schedule another one of these. That'll happen. That'll kind of go back like this, and then notice that none of these events are ever going to get scheduled. In fact, one of the powerful things about these event graphs is that you could, by just looking at the event graph, we can apply some elementary graph theory or network algorithms, no matter how complicated it is. And for any event to have a possibility of occurring, there must be a directed path from a run event to that event. And if there isn't, and then now here it's easy to see, but in a complicated model, it may not be so straightforward. But in any event, I mean, here we have we basically have sort of two graphs here. So what the heck is going on? What's missing? Well, what's missing is what happens when this event occurs, the end service at the first station. It may schedule a start service at the first station again, but what else does it do? Yeah, it's going to schedule the next arrival, and we're assuming that the time it takes to get from that first station to the second is negligible or zero. Okay. Those are assumptions we're making. That's something that we could maybe examine. Okay, so now there is a possibility of these occurring, and basically this is the model. This model captures what was said before. And this may seem very, I mean, I hope I'm not going too slowly, but it's, but again, the meta thing is we had a situation, it was similar, but a little different than the first one. What did we have to do to capture that? And hopefully I got it correct. Okay, so there's a cleaner way to look at it. All right, so now let's look at this. When we look at our particular situation, I said one of the assumptions is that the time it takes to go from the first station to the second station was, it's always going to take a finite amount of time. But even if your service times and inter-arrival times are in minutes, and the time to get to the next station is in seconds, then it's essentially zero. Just as in our multiple server queue example, the time it took to get from the queue to the server was modeled as zero. In fact, it might take like a second, like if you're at one of these ticket things. But compared to the amount of time it took you to get service, which may be minutes or maybe hours, or negligible. So, but what if it isn't negligible? What if it isn't negligible? Well, what can we do? Well, we can add another parameter as an additional parameter and say, okay, if it takes a certain amount of time to get from the first station to the second station, then all we need to do is add a delay on that edge that we had, and now it's captured. So that's one, so maybe maybe the first station is like TSA at an airport, and the second station is like your gate. So it's like, at least I've never been in an airport where it didn't have to kind of go halfway around the thing to get to there. There's a Murphy's Law about that somewhere. I don't know. Okay. Now here, another use case is this one, and this is kind of a very useful one. That we only go to the second station with a certain probability. And the use case that I have for that is something like rework. In other words, say the first station might be you're fabricating something, and then after you fabricate it, you inspect it, and that's part of the service time. And if it passes, then you just kind of send it on. But if it doesn't, like if it fails in a certain way, then it needs to be reworked, but you're not reworking it. It's like there's a separate rework facility or server who does that. Okay, so it's a simple, this, you can go way down the rabbit hole with this kind of stuff. But this also introduces a useful little modeling snippet, which is when I have a certain probability of scheduling the next event, how do we model that? So there are a number of ways, but the most straightforward is to define a sequence of uniform random variables, add, well, a certain probability. So if P is the probability of, in this case, of rework, then the condition that you put on is simply U is less than P. So if I be, why? Because this will be true with probability P. And what does that look like? Okay, so well, here's, we add two parameters, one, that probability, and the second, this uniform set of random variables, and the Boolean condition U is less than P on this thing. In other words, when we finish service at the first station, we don't always go to the second station. We only do if rework has happened. And this is the simplest model of this. If we're kind of, okay, I mean, if we're sort of speaking of TSA, this might be the probability that they kind of take you out and do the wand scan or something, something like that. There usually isn't a queue for that, but that same type of deal. Okay. So those are, give me my mouse here, come on. So I can't stop the share because, let's see if this will help. Come on. That is bizarre. See, it's not giving me my mouse. Let's see if I can. Yeah, it will only show the mouse. It only showed the mouse on the screen, but I needed the mouse to stop the share. So it's kind of, it's like that. Probably told you about that game I was playing once, where it's like I had to get into a building and the guard stops and says, "You need a pass." And I said, and the character says, "Where do I get a pass?" He says, "In the building." So, okay, so that's a tweak on that. Any questions about this? This was fairly straightforward. Any questions from the remote? Okay, so that is that. And I will see you tomorrow.